So dear students, welcome you once again. I'm Meghamala, working assistant professor from Institute of Aeronautical Engineering, ECE department. And today I'm going to share something about register transfer level in Verilog. So basically, what does this register transfer level means? Register transfer level in the digital circuit design, it says that it is an abstraction which models a synchronous digital circuits in terms of data flow between hardware register and logical operations performed on those signals. So here, one thing we have to remember regarding this register transfer level, it means that it is a design abstraction which models a synchronous digital circuits. It models some synchronous digital circuits in terms of data flow. Okay, in terms of data flow, it models the digital circuits, synchronous digital circuits in terms of data flow between hardware registers and logical operations performed on those signals. So, between hardware registers and the operators. Between the registers and the operators, logical operators. It is an abstraction where it models some digital circuits in data flow modeling. Okay, by using in terms of data flow modeling between the registers and as well as the operators. And then RTL, register transfer level abstraction, is used in HDL. So in hardware description language, we use this level of abstraction, that is register transfer abstraction, to create high level representations of the circuit. So in order to create something which is high level of abstraction, that is a high level of representation, most of the times, or else we use in HDL, will be going forward towards the register transfer level, and from where low level representations and ultimately actual wiring can be derived. So here this RTL, the abstraction, this particular abstraction will help us, or else it is used in HDL in order to create a high level representation of a circuit. Okay, high level representation of a circuit, from where low level representation, that means what? There is a transformation from low level towards the high level. So from low level representations towards the high level representations to create some high level representations, and ultimately actually wiring can be derived. Okay, so just to wire, or else just to connect from the low level towards the high level, we are going towards the register transfer level. So this level will make us to design the circuits in order to create a high level of abstraction, that is a high level of representing the circuit. And then designing at the RTL level is a typical practice in modern digital design. So compare in the reality, okay, in the real time configuration, we say this RTL is a typical practice in modern digital circuits, okay, in digital design. In RTL design methodology, different types of registers such as counters, shift registers, serial in, parallel out, parallel in, serial out are used as a basic building blocks for any sequential logic circuits. So most of the times, or else in maximum approaches, we can create or else we can design the circuits based on the counters. We can design the circuits such as counters, registers, serial in, parallel out, and parallel in, serial out systems, or else blocks, and as well these are used for the basic building blocks of the sequential logic circuits. So as these are considered as basic building blocks of the sequential logic circuits, so by using this high level of abstraction, that is high level of representation of register transfer level, maximum times we will be going towards to design this such methodologies. And then on the other hand, I can say that synchronous sequential design methodology. Okay, synchronous sequential design methodology, different logic gates and different memory elements such as flip-flops to store the information, to store the state of a circuit at any time is used as a basic building blocks for sequential logic circuits. So here in two logic circuits, that is whether in the combinational logic circuits as well as in the sequential logic circuits, the important play that RTL is playing is it says that not only in the combinational sequential circuits, that is not only in the not only for the counters, shift registers, or else the serial in parallel out or parallel in serial out, in all such cases, not only in the designing parts, also we can make use, or else we can design in the sequential circuits, such as like flip-flops. Most of the time the flip-flops will be considered because these are the memory elements where they can store the 1 bit of memory, and at any time they store the state of that particular memory as well. So these are used as the building blocks for the sequential logic designs. So here in this particular figure, if you observe the synthesis from the Verilog, okay, this is a Verilog. From the Verilog, the synthesis is occurred because using the RTL. So with the help of this register transfer level, we can make use, or else we can create something new, or else we can create something high level of abstractions from the low level. From the ground level, we can create something great, that is a high level of representing the designing of such sequential or the combinational circuits. And then a synchronous sequential circuit. So the synchronous circuit consists of 2 elements. So what are those 2 elements? This is the registers and the combinational logic. So synchronous circuit, it consists of, obviously we know that synchronous circuit consists of the combinational circuit, and as well as the memory elements. So these memory elements consist of flip-flops, latches, and the registers as well. Okay, flip-flops, latches, and the registers as well. Feedback is been given, and these are the inputs, and here the output will be observed at one end of the combinational circuit. So the synchronous sequential circuit, so the synchronous circuit consists of the registers, those are nothing but the sequential logic, and as well as the combinational logic. So we will see how this register transfer level will make us to design the design, will make us to help in order to design some basic blocks like counters, as we discussed earlier, like counters, flip-flops, and also the serial in parallel out blocks and parallel in serial out blocks, and so on. So registers. So registers is a sequential logic where the registers synchronize the circuit's operations to the edges of the clock signal. Okay, so the basic, the key role that these registers, or else this sequential logic playing in this RTL is that they synchronize the circuit. Registers will synchronize the circuit to circuit operation to the edges of the clock signal, and are the only elements in the circuits with memory properties. So as I said these registers are nothing but the storage devices. Not only with the registers, we can go with the flip-flops as well, flip-flops and latches as well. So here, these memory elements, what does they do is they do just synchronizes. They synchronizes the circuit operation to a clock signal with respect to the clock signal. Obviously, certainly that the clock signal involvement is there because we are using the memory elements, right? So each and every flip-flop and the latches, they use the memory, they use the clock signal as well. So even for the registers are nothing but the group of flip-flops. So when the group of flip-flops are considered together as a one part, then we are saying that it's a register. So most of the times, or else in maximum area, we are using the memory elements. So in the sequential logic, as we are considering the registers are the basic building blocks, so there we are coming across a clock signal, and they are usually implemented as D flip-flops. So basically, prominently we are going with the D flip-flops compared with the SR flip-flops or master slave flip-flops and T flip-flops. Maximum times we are using this D flip-flops. And then coming to the combinational logic. So this combinational logic it performs all the logical functions in the circuit. So this is a combinational logic. So it completes, or else it functions, it gives out all the logical functions in the circuit, and it consists of the logic gates. So this combinational circuits consist of logic gates, whereas sequential logic consists of the memory elements like registers, flip-flops, and latches. So the combinational logic circuit, what it does is it performs all the logical operations with respect to the logic gates. Okay, and logic gates are nothing but all the different types of gates which are present in the Verilog library, Verilog primitive, gate primitives. And in HDLs, the designer declares registers, okay, in HDLs, in hardware description languages. Basically, the very first and the foremost thing the designer will do is it declares the registers which roughly corresponds to variables in the programming languages. So all the registers will correspond some values or else variables. Okay, in order to write some code, what do we do is we need some inputs and we need some outputs. So all the inputs can be acquired, or else all the inputs can be downloaded, or else can be taken from the libraries, right? Can be taken from the register, different sort of registers. So here it roughly corresponds to variables in the programming languages. So the registers, whatever the content that it is having, so the content or else the variables the registers is holding can be used or else can be taken up in order to code some the programming language, and describes the combinational logic by using constructs such as if, then, else and arithmetic operations. So in order to design or else in order to design some circuit, we have to go make use of the constructs. We have to make use of the construct. So we have many types of constructs in our Verilog library, like if, then, else and arithmetic operations. Coming to the operators, already we have discussed in the module 1, like there are many types of operators such as arithmetic operators, logical operators, relational operators, concatenation and rational operators, case sensitive operators, and so on. So in order to write some program, okay, in the programming level or else in the coding part, we have to come across different types of constructs. So here also in the hardware descriptional language, we are saying that the designer being a designer, he has to consider some registers, where the registers will hold some information or else where the registers will hold some data which is applicable for the inputs. Okay, and then after that input, it could be in terms of variables or the values that it contains. So the variables for in order to write a programming language, and this describes also whatever he does, it describes combinational logic by which constructs such as if, then, else and arithmetic operations. So in order to perform this such operations, or else in order to by considering all such constraints or else all such constructs, we can easily develop a block, or else we can easily develop some circuit. Okay, some digital circuits can be easily developed, and then this level is called the register transfer level or RTL. So all such mechanism, what is happening inside, that means what regarding the constructs or else regarding the memory elements, regarding the considerations of different values or variables from the registers, all these things can be done under one roof, that is a register transfer level or RTL. So the term RTL focuses on describing the flow of signals between the registers. So basically, as the name indicates, that register transfer level. So register transfer level is nothing but some values or some data is being transferred among the registers, between the registers, right? So here the flow of signals or the flow of memory, the flow of data between the registers is nothing but the register transfer level. So all the memory or else the flow of signals which contains some memory can be done by using the register logic or else the sequential logic or else a combination logic. So if you are going as per the sequential logic, remember that the memory elements could be of flip-flops. Basically, most of the times we are making use of the D flip-flops. If you are going as per the combination logic, remember that your memory element should go as per the logic gates. And then, so this RTL describes description can usually be directly translated. So it can be directed as it is RTL, register transfer language, register transfer level, right? So directly it can translate into an equivalent hardware implementation file using EDA tools for synthesis. Yes, so obviously when it comes to the synthesis process, analysis is one part and the synthesis is another part, right? So in the synthesis part, we need some tools to execute the program. So we need EDA tools are very much applicable for the synthesis process of any kind of mechanism, that is either the synchronous sequential circuits or else for asynchronous sequential circuits. So with the help of EDA tools, we can execute or else we can make use of the hardware implementation easily. And then the synthesis tools also performs logic optimization. So here, not only for the synthesis of the analyzing, synthesizing, and also for the logic synthesis or else for the logic optimization, can make use of all such things can be easier. And then at the RTL level, or else at the register transfer level, some types of circuits can be recognized. Okay, so as I said you, this is one way of abstraction. There's a higher way of abstraction where it creates a high level of implementation. So here at this RTL, okay, at the RTL, some types of circuits can be recognized. So some types of circuits can be recognized easily at this RTL level. Okay, and then if there is a cyclic path, okay, when you are designing some devices, when you are designing some module, or else when you are designing some digital circuit. So while in the part of designing, if you come across there is a cyclic path, if you come across a loop or a cyclic path of logic form, registers outputs to input, then the circuit is called a state machine or the sequential logic. So when you have designed some circuit, or else when you have designed some module, and that module consists of any sort of cyclic representation. That means what? I can remind you this Mealy and Moore machine. So in this Mealy and Moore machines, we feel there is a feedback, right? So feedback from the sequential, feedback from the memory elements can be given as the input to the combinational logic, right? So if you see such cases, or else if you find some feedback like structures, or else if you find some loop like structures, then such kinds of machines is represented as a state machine or the sequential logic. So when it comes to if you come across anywhere state machines, remember that Mealy and Moore machines. Why? Because those two kinds of machines, we can see the feedback, right? We can see the feedback from the memory elements as given as inputs to the combinational level. So if you find anywhere in the RTL, if there is a cyclic path which is observed, then such machines are called to be as a state machines or the sequential logic. And then if there are logic paths, okay, if there are any logic paths from register to another without a circle, then it is called a pipeline. So here sometimes in the designing part, we see some machines are with the cyclic path, or else we see some machines are with the the loop kind of thing. If you observe, then that machines are called as a state machines or else a sequential logic. Or if you don't find any loop like structures, if there is no cyclic path, if you don't find any cyclic path, then it is called as a pipeline. Okay, so the pipeline does not consist any loop-like structures or else a feedback structures. Directly input will be given and everything will be sorted out inside the module, and output can be observed out. If not that cases, then if you find any sort of feedback path is given or a cyclic path is given, then observe that there is a state machine. Okay, if not, if there's without a circle, then it is called as a pipeline. Then coming to the RTL circuit design cycle. So what is this RTL circuit design cycle? So here this RTL is used in the logic design phase. We know that for the designing of some block with respect to the logical synthesis, we go with the best way is to implement is by using RTL. So RTL is used in the logic design phase of the integrated circuit design cycle. So in order in the area of the integrated circuits, in integrated circuits area, if you are designing any sort of digital circuits, that is with respect to the logical designing, then the better way is that RTL will make us to it help us to design some module based on the logical synthesis, okay, logical design. And then an RTL description is converted into a gate level description of the circuit by logical synthesis tool. So here, if you observe this statement, it's talking about the conversions. Okay, it's talking about the transformations. If the RTL description, if it want to convert it into gate level description. Okay, from the data flow to the gate level description. Okay, if you want to convert something into gate level description of the circuit, we can use the logical synthesis tool. So this logical synthesis tool will help us to convert something into the gate level description. And then the synthesis results are then used by placement and routing tools. So after finding, or else after synthesis, after logical synthesis of the gate level representation, and here the synthesis results, whatever the results that we have obtained, that results are then used by placement and routing tools to create a physical layout. So in order to create some physical layout, what happens is logical synthesis will helping us to make, or else helping us to do something with respect to the placement and routing tools. So placement, it's like an interconnection between synthesis, logical synthesis tools, and as well as the placement and routing tools, and then final phase is all about the physical layout. So physical layout can be observed with respect to the placement and routing tools, and this placement and routing tools can be considered with respect to the synthesis, logic synthesis tools. Okay, so logic synthesis tool is nothing but, if you want to convert something, the RTL is about to convert something to the gate level description of a circuit by using this logical synthesis tools. Okay. And then this logic simulation tools may be used as a design's RTL description to verify its correctness. So now after finding out the physical layout, after getting the physical layout, now we want to examine this physical layout, whether all the layout, or else the layout consisting of all the elements, all metals and the color coding is everything is fine or not, we want to check. And then now logical simulation tools will help us to check about the correctness of, it will help us to verify the correctness of this particular physical layout. So here the logic simulation tool will help us to check the correctness of, or else will help us to verify the correctness of the particular physical layout. And then in RTL design, the basic building blocks are register, multiplexers and and as well the adders. So in register transfer level, as we have discussed, the register transfer level is to create a high level of description, whether the RTL can go as with the registers or the sequential logic, and also with the combinational logic as well. So in the sequential logic, we have discussed about the flip-flops, or the memory elements are the major basic building blocks, whereas in the combinational logic circuits, we have discussed that basic logic gates are the basic building blocks, right? So here in the RTL design, the basic building blocks could be either multiplexer, registers and adders. Why? Because multiplexers, registers and adders, they have the storage devices, storage elements like flip-flops, latches. Okay, and so that we are calling that in RTL design, the basic building blocks are considered to be the registers, multiplexers and as well as the adders. And in RTL design is much closer to the behavioral design of the logic circuit, as it models the data flow modeling different registers, and hence it is much more intuitive. So here the sentence says that RTL design is much more closer to the behavioral design of logic circuit. So RTL, that is register transfer level, it is much more closer. There is a similarity. Okay, the RTL has some similarity with respect to the logic circuit, the design of logic circuit. Because why? Because it models the data flow among different registers. Why we are saying that there is a similarity between RTL and the design of logic circuit? Because there are the maximum similarities can be seen between these two, RTL and as well as the design of logic circuits. So the similarities are found with respect to the data flow. Okay, with respect to the data flow among registers, and hence it is much more intuitive. So it is much more effective when it compares to the RTL and as well as other level of abstractions as well. And finally, RTL modeling allows us to synthesize complex circuits with a large number of states with much more ease to compare to sequential logic design. So here RTL, it not only models the basic models, it not only design the basic models such as adders, subtractors, or else multiplexers, or else we can say the register, different types of registers, but also it can go, or else it gives its contributions towards the synthesizing of the complex circuits. Okay, in order to synthesize the complex circuits, RTL will make us, or else RTL will help us to synthesize such complex circuits as well. And it can be compared to the sequential logic design as well. And now coming to the power estimation techniques. So what are these power estimation techniques is the most accurate power. Power plays a vital role not only in the electronic devices but also in all the other aspects. Okay, in all the other aspects power plays a vital role. The less power is consumed, the more effective it will be the output. So here, the power estimation techniques, if you consider in the RTL designing or else in the RTL design, the most accurate power analysis tools are available for the circuit level. Okay, so in order to estimate the power also as well, we have in the Verilog the power estimation tools as well. So the power estimation tools are available at the circuit level, but even with a switch rather than the device level modeling. So if you consider a switch level and the device level modeling, we see the power estimation tools are considered, or else we can see the power estimation tools are available in circuit level rather than in the design level modeling. So the tools at the circuit level have disadvantages, but there is a disadvantage when you consider the power estimation tools at the circuit level. So in this case, we can go, or else we can choose the power estimation tools for the design level modeling. Okay, why? Because we have some disadvantages in the circuit level. Then they are either too slow or too much. They require too much of memory. So one of the disadvantage when you are considering the power estimation tools for the circuit level is that either they can be too slow. Okay, the implementation of, or else the power estimation, the consideration or else the observation of the power estimation is too low, or else the consumption of memory will be too high. Okay, too high consumption of memory, or else either it could be the processing would be the too slow. And then the majority of these simulators are like the majority of the simulators like SPICE and used by the designers for many years as performance analysis tools. So here we all know that in VLSI technology, in the VLSI world, we use the simulator like SPICE. Okay, so this simulator will help us, the designer will help the designer, also it is maximum most of the time used by the designers for many years at the performance of analyzing tools. Power estimation tools, we are using the SPICE simulator. And then due to the disadvantages, so due to this too slow and too much high memory consumption, due to these disadvantages, gate level power estimation tools have begun to gain. So here there are some disadvantages we found in the circuit level, right? So in order to overcome this, what do we say, disadvantages, gate level power estimation tools have come into existence. So gate level power estimation tools have begun to gain some acceptance, which is faster. Why we are going for the gate level power estimation tools? Because they have some advantages, like it is faster and the probabilistic technique have begun to gain a foothold. So one of the major constraint that we can consider here in this gate level power estimation tool is it is faster. Okay, so it is faster. As it is faster, so we can go for the gate level power estimation tools compared to the other estimation tools. And then, but also it has a trade-offs. Okay, it also has a trade-off, considering that speed up is achieved on the cost of accuracy, especially in the presence of correlated signals. So in terms of correlated signals, we see that the speed is achieved. The swiftness of that particular module can be achieved, and also the cost of accuracy. The cost of accuracy is also achieved in the when the correlated signals, in the case of correlated signals. And over the years, it has been realized, okay, over the years, it has been realized that low power designs cannot come from the circuit and gate level optimizations. So here, one of the major factor that we are talking about is power, right? Power estimation tools, power. So what we are saying, over the years, okay, from the past era, we can say that we are realized, or else it has been realized that low power design cannot come from the circuit and gate level optimization. So why we are saying this, why we are pondering on this particular sentence, that is low power designs cannot come from the circuit and gate level optimizations. Yes, of course, that is true, because in the previous slide we have discussed that using circuit level description, we say that it is too slow and the consumption of memory is too high, one of the disadvantages, right? But we are saying that over the years, we say that the low power design consumptions cannot be considered for this circuit and the gate level primitives or as optimizations, because in contrast, system architecture and algorithm optimizations tend to have largest impact on power consumption. So in contrast, that means what we have discussed something saying that when it comes to the circuit analysis and device analysis, in the circuit analysis the power consumption is maximum, and it is very slow, okay, too slow. And also one of the constraints that we have discussed is the memory. Okay, the consumption of or else utilization of memory is maximum. Okay, those are the disadvantages. But to be frank, or else the fact is that to be frank, over the years we are saying that the power consumption is minimum for the, or else the minimum power consumption can be seen in the circuit and as well as a gate level optimization, right? But in contrast, or else in the other way, we can say that the architecture and the algorithm optimizations can have architecture and algorithm optimizations can tend to have the largest impact on power consumption. This is true. Okay, this sentence is very true that for the architecture and as well as the organization optimization, algorithm optimization, in order to create some structure, right? In order to create some structure, sometimes we have to take some algorithms, right? So algorithms, assumptions, or else algorithmic optimizations, and also the architecture of that particular design make sure that the largest power impact or else the largest impact on power consumption, obviously, which is true. And therefore it has been shifted to tool developers inclined towards high-level analysis and optimization tools for power. So now it has been like a challenge for the tool developers. So it's been like a challenge for them that in order to overcome this power estimation constraints, they have to develop this tool such that the power consumption should be very low, and also the memory management should be considered, and all those specifications should be clear, and they have to meet the required analysis, right? So now it's all about the tool developers, where they have to concentrate more on the power consumptions, they have to develop the tools with regard to the power assumptions. And then coming to the gate equivalent technique. So gate equivalent technique is a technique based on concept of gate equivalence. So it's a technique purely contains, or else it is a technique purely it's a concept of gate equivalence. The complexity of chip architecture can be described approximately in terms of gate equivalence. So how the gate equivalent can be observed or else can be seen? How is with respect to the complexity of chip architecture? For suppose, being a designer, if you have designed some digital circuit, and that digital circuits you have designed with numerous number of chips, right? So what happens if you are designing that particular module with a number of chips? The complexity is maximum. The complexity, it could be in terms of power consumption. The complexity, it could be of interconnections. The complexity, it could be with respect to the algorithms that you are using. So in all this scenario, we see the complexity, right? So the complexity is purely based on the gate equivalence technique. And now, where the equivalent gate count specifies average number of reference gates that are required to implement the particular function. So here we have to concentrate on, in order to overcome or else in order to omit this complexity, in order to get rid of from this complexity, we have to make sure that the equivalent gate count specifies. So how many gates? The count of gates should be considered. So equivalent gate count, and as well as the average number of reference gates. So equivalent gate count is one of the factors that you have to consider, and one more factor is the average number of reference gates. So what are the basic gates that you are considering in order to design some module, and also how many number of gate count, okay, how many number of gates total you are considering, and how many number of gates are playing a vital role. So all these considerations we have to consider and then design a particular digital module. Then the total power required for the particular function is estimated by multiplying the approximated gate equivalence with the average power consumed per gate. And now this is just an arithmetic way of representing the power consumption among the gates, between the gates. So it says that the total power required. So the total power required is equals to, it is a function of estimated by multiplying the approximated gate equivalence, okay, approximated gate equivalence product of with average power consumed per gate. So average power consumed, power average. So it is a power average consumed per gate. So this is just a little bit way of understanding, a keen way of understanding of how the power consumption is made among the gates. So here the total power consumption based on the gate equivalent is given as, it is nothing but the average of the equivalent of average gates. It's a product of equivalent of average gate along with the average power average per gate. Okay, power average per gate. So how many gates that you are considered, and for example, if you are considering 10 gates, okay, in order to construct some module, if you are considering 10 gates, out of 10 gates, 4 gates are the reference gates, isn't it? 4 gates are the basic gates, so reference gates. So totally you're considering 4 gates are the reference gates and 6 gates are the normal gates where they are used for the interconnection purpose. Okay, so here now you have to concentrate on the power consumption of each and every gate. So you may think that more power can be given or else can be consumed by these 4 reference gates, and then less power consumed by with this 6 alternate gates, right? So this is a small expressions where the total power consumption, how the total power consumption can be made or else can be observed with respect to the gate equivalent technique. And then the reference gate can have any gate, that is, for example, here he has given 2 input NAND gates. Okay, 2 input NAND gates. This technique is distributed in the following type. So the power estimation techniques, it goes with this with respect to the gate, with respect to the, what do we say, with respect to the gate equivalent technique, right? So now we will see there are 2 such cases where we can observe the power modeling. Okay, one is with respect to the class independent power modeling, and the second one is with respect to the class dependent power modeling. So one is with respect to the class independent power modeling. So this class independent power modeling is a technique which tries to estimate chip area. Okay, class independent. Remember, we are going with 2 classes, 2 cases. One is with class independent and the second one is class dependent. Class independent is it tries to estimate the chip area, speed and power dissipation. Okay, it ponders on, or else it concentrates more on 3 factors, that is chip area, speed and as well as the power dissipation based on information about the complexity design in terms of gate equivalence. So it totally depends on the complexity of the gates. Okay, complexity of the design in terms of gate equivalence. So if the design is more complicated, then we have to consider or else we can estimate the power distribution among the chip area, speed of the module and as well as the power dissipation. And then the functionality is divided among different blocks. Okay, so the functionality it's like divided into different blocks, but no distinct is made about the functionality of the block. That means what? Here we can say that the class is independent. The class is independent where we cannot compare with the other thing. That means what? It is made functional. The different blocks, the functionality is made different among the different blocks. It is not together as one block. It is made, the functionality of different blocks can be observed independently. So that's the reason we are calling it as class independent. So if it is observed, if it is a basic block, okay, a circuit, a module that you have modeled. So in this module, you have come across many devices, many models from M0 to M6. So here, being a designer, what I have to consider each and every block as a independent block. Okay, so each and every block as independent block I must consider, and I have to check with all the aspects like speed, chip area and as well as the power dissipation. That's how I can say that this is a class independent power modeling. Then this technique completes the following steps. So if you are choosing this sort of case in order to know the power dissipation or also power estimation, then you have to follow all the steps. So step 1 goes that identify the functional blocks such as counters, decoders, multiplexers, memory elements. So first and foremost thing we have to identify. As I said if this is a circuit diagram or if the circuit that you have modeled, then in which module that you are erasing the power dissipation or as a power factors. So you have to thing, or else you have to concentrate about the blocks, or as a segregation of the segment of the different blocks among the different blocks. So you can say this is a counter, and you can say this is a decoder, you can say this is a multiplexer. And now in the multiplexer you have to see whether the chip area is proper or not, or its power dissipation is maximum or minimum, and the speed of the particular device, or else the speed of this multiplexer is relevant, or else is moderate, or else if it is going high or not. So all these considerations can be seen individually. That's why we are saying that there is a chip independent power modeling. And then next step is assign the complexity in terms of gate equivalence. And now we have to assign the complexity. We have to look for the, we have to check, okay, using the gate equivalence technique, we have to check in which model the complexity is maximum, in which model the complexity is erased for due to some what factors. Okay, all these things can be done by using the step 2. So assign a complexity in terms of gate equivalence, that is the number of gate equivalents for each unit, okay, type are either taken directly as an input from the user or fed from the library. So here the number of gate equivalents. So something that you have come across, or else something that you have found the complexity in the multiplexer. So you have to remove that complexity. So what we have to do is, with the help of library, from the library we can consider the gate equivalence technique, or else gate equivalence, different types of gates can be considered, or else we can directly take from the library, or else from the gate equivalence technique as well. Then coming to the second case, that is case dependent power modeling. So case dependent power modeling is totally better than the previous approach. So here, when you compare the class independent power modeling and class dependent power modeling, the class dependent power modeling is much better. Okay, if you want to consider, you can go with this class dependent power modeling. So it takes an account, into account, customizes the estimation techniques to different types of functional blocks. So it just look for each and every module, okay, in the circuit, or else in the model that you have modeled, it will check each and every block, okay, each and every block. So it customized estimation techniques to the different types of functional blocks. So each and every block, each and every functional block, it will just take a check. And then, therefore, it is trying to increase the modeling accuracy. What happens for each and every time, if it is checking each and every block, what happens is the accuracy is being increased. So the model increase, the accuracy is being increased, and then which wasn't in the case of previous techniques such as logic, memory, interconnects, and clocks. So if you compare this clock, class dependent power modeling technique with the class independent power modeling technique, there are many advantages, and it is very easy to consider this power modeling technique, because here we can model, okay, due to the accuracy, or else if you want to increase like here increase the model accuracy, the accuracy can be increased. When the accuracy is increased, we can say that the case independent power modeling, the accuracy is very less, the efficiency is very less, whereas in the case dependent modeling, the efficiency is higher. So in case of previous techniques such as logic, memory, interconnects, and clock. So in this scenario, or else in this particular case, we can check, okay, we can check easily in each and every functional block. We can check about the memory, we can check about the logic, we can check about the interconnections among the peripheral devices, and as well we can check about the clocks. Okay, and then the power estimation is done in a very similar manner to the independent case. So here, when you compare with the independent case, in the dependent case, the power estimation can be done very easily. And then the basic switching energy is based on 3 input AND gates and is calculated from the technology parameters. So the basic switching energy is based on 3 input NAND gates. Why this 3 input NAND gates? This is the example that we have considered. So if you are considering any sort of gate, then the switching energy can be considered from that gate itself as well. So here example, gate width, torques, and metal width provided by the user. So these are different constraints. Okay, These are different constraints. Then these constraints will help us to know the power estimation of different functional blocks. And so here these are the variables, or else these are the values or the variables that we can obtain from the primitives. And then pre-characterized cell library techniques. So what is this pre-characterized cell library techniques? The name itself, we can understand from the name, from the heading itself, is pre-characterized cell libraries technique. So it is a technique where pre-characterized cell libraries. So this technique, it customizes what the power estimation of various functional blocks, various functional block by having a separate power model for logic, memory and interconnections. So it will have a separate power model. So this is pre-characterized cell libraries technique. So this technique is one of the technique based on the power estimation, and this technique will help us to know the power estimations, or else this technique will help us to know the power problems, the problems which are arising from the power consumption in each and every aspect, that is in the logic, in the memory and as well as in the interconnects. And then these suggest a power factor approximation. So it considers, or else this power pre-characterized, this technique, pre-characterized cell library, PCCL. So this PCCL, it suggests a factorization, or else it suggests some approximation, that is power factor approximation method for individually characterizing an entire library of functional blocks. So individually characterizing the entire block, individually from the block, individual module, individually this technique, PCCL technique, will characterize. Okay. So characterize such as multipliers, adders, etc. instead of single gate equivalent model for logic blocks. So as I said it is like a, we can consider, or else we can compare it with the, what is this? We can compare it with this one, previous one, class dependent power modeling. So we can consider this PCCL with clock dependent power modeling. So PCCL with clock dependent power modeling. Clock dependent. So here we can say that the power factor approximation, it is a method for individually characterizing the entire library of functional blocks. So for entire library of functional block, individually we can characterize. Okay, individually we can come up with the different things like based on the power. So power factor approximation. And coming to the advantages of PCCL, pre-characterized PCCL technique. Okay, PCCL technique provides the following advantages. So the advantages goes with the customization. The customization is possible in terms of whatever complexity parameters which are appropriate for that block. So here the customization is considered, or else it is what is this? It is possible. The customization is possible of whatever complexity parameters which are appropriate for that block. So the parameters which are pertaining to that block, the customizations can be made easily and possible for that particular block. And then for a multiplier, the square of the word length was appropriate. So here it's an example. Example he has given, saying that for multipliers, usually we can say that the square of the word length was appropriate. So you can observe the square of the word length. Okay, what is the word? What is 16-bit, right? So square of the 16-bit. Square of the 16-bit was appropriate for this particular example. And the storage capacity is used in the bits for memory, and the word length is alone adequate for input-output drivers. So here for memory storage, for memory we use bits. Okay, right? Bits are used in the memory. Storage capacity, for the storage capacity, bits are used for memory, and for the word, okay, word length alone is adequate for the input output drivers. So for input output drivers, we goes with the word, that is 16 bits input output drivers. But whereas for memory, we'll take in terms of bits. And so this is all about today's topic, that is about the register transfer level. So in the register transfer level, we have discussed what is register transfer level and how it is going to help us for all the designers, and what sort of tools will help us to design the layout. Okay, design the layout. There is an interconnection between the synthesis tool, logic synthesis tool, placement and routing tool, and as well as the physical layout. And then we have come across the power estimation techniques. So in the power estimation techniques, we have come across two kinds of two cases. One is with the gate equivalent techniques, where this gate equivalent techniques is modeled with respect to the gate equivalence, gates, with respect to the gates, and also one more thing we have discussed, that is a class independent power modeling, class independent and class dependent power modeling. So when you compare class independent and class dependent, remember that class dependent is more accurate, or else it is more efficient than compared with the class dependent power modeling, because in the class dependent power modeling, each and every block can be observed keenly. Okay, each and every functional blocks can be observed, and if each and every block is having some problem based on the power, then they can be rectified easily by using a calculation. Okay, so total power estimation is nothing but it is a equivalence of the gate. Okay, it is equivalence of gate arrays. See here, it is a equivalent of gate arrays along with it's a product of equivalent of gate equivalent of gate count and the total average power with respect to the per gate. Average power per gate, it's a product of average power per gate and the equivalent of gates, that is nothing but the total power. So so like how we can estimate the power, total power can be estimated in terms of both independent, class independent, and as well as the class dependent. But if you compare the class independent and class dependent, always class dependent is more beneficial, always it is more accurate. The efficiency of the class dependent is more accurate or else efficient than compared with the class independent, because in the by using class dependent we can easily sort out the power estimation problems by considering the individual functional blocks, whereas the class dependent, in the class independent, we have to concentrate on it is like interconnecting from one block to the other block. And also we have discussed something about the design cycles. So these design cycles we have discussed, like it's an interconnection between the physical tools, synthesis tools, and a physical layout. So it has to go to it has to go to all this process. This tool will help us to convert from one to the another. Okay, and then what is this? There is a small difference between the cyclic path and the as well as without cyclic path. If it is not without cyclic path, then we are saying that it is called a pipeline. And then if you find any cyclic path, or else if you find any sort of loops, then such sort of machines comes under the state machines or sequential logic. So say in the state machine, we have discussed about Moore machine and Mealy machine. Okay, and coming to so this is about the register transfer level in the Verilog. I hope you all understand well. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.